Look closely at high-end hardware and you'll find a quiet reality. The vast majority of its surface will never feel a human hand. Yet, out of all that sleek real estate, a few highly specific square centimeters absorb almost 90% of the physical contact. Those tiny, concentrated zones of friction demand a completely different set of rules. They need harder finishes, demand custom textures, or specific chemical resistance to survive thousands of interactions. Despite this extreme difference in wear and tear, manufacturing usually operates under a convenient illusion. We treat the entire object as if every square inch experiences the exact same life. The root of this problem starts early. During the concept phase, designers rarely map out where the user puts their thumbs. Instead, finish requirements get handed down as blanket rules, assigned per material, part, or color, ignoring how humans actually behave. The first consequence of that shortcut is obvious over time. The product wears out in patches, leaving ugly, degraded scars exactly where the finish is eroded away by daily use. The alternative is vastly more expensive. You apply a premium, highly durable coating across the entire chassis, wasting money to protect vast stretches of metal or plastic just to cover the one button that actually needs it. Operating in this vacuum of behavioral data forces a brutal choice. You either accept inevitable aesthetic decay, or you burn through your budget paying for armor the product doesn't need. So, who actually has the data to predict exactly where human hands are going to go? The behavioral data needed to draw this map comes from an unlikely source: accessibility lawyers. The data sits inside the U.S. Access Board and its ADA guidelines on operable parts. Their regulations meticulously inventory where hands go on a massive variety of everyday objects, covering everything from thermostats and light switches to communication receptacles and ATMs. What they've published is an enumerated, highly specific database of human physical behavior, and it is sitting right there in plain sight, completely free. While most teams treat regulatory law as a list of constraints, it functions as a rigorous description of user behavior, one that is often more precise than a designer's own assumptions. The legal code partitions a single physical object into two distinct zones. First is the operable zone, actively engaged by the user, governed by exact reach ranges and dimensional constraints. Then the rest is merely present, completely exempt from those stringent finish requirements. This logic is backed by deep scientific archives. Human factors data from OSHA detail exact posture limits and physical interaction ranges for workstations and displays. The abrasion tests and the ergonomics data already exist to map out precisely where an object will wear. But these tools only work if designers integrate them at the right time. Taking advantage of this map means implementing what the industry calls a zoned finish. Giving one specific high-touch area a different specification is rarely just a quick surface change. It requires structural adjustments, a new insert, a masked process, or an entirely different tool to handle the part split. Because you are changing the manufacturing process, you inevitably leave a physical, visible boundary between the operable and non-operable zones. That boundary becomes a permanent design element. It forces the product to make a clear physical statement about exactly where it expects to be handled. This brings us to a strict manufacturing deadline. The decision to zone a finish and carve out these boundaries has to happen early, precisely when the part split is finalized. If a design team waits until after the manufacturing tooling is cut to finally discover their touch map, their structural options are permanently gone. At that stage, you are forced right back into the initial error, either coding everything expensively and wasting the budget, or accepting patchy, degraded wear. To avoid this, those boundaries must be engineered perfectly during the concept phase, using predictive data to foresee physical interaction before anything is actually built. Design decisions are as cheap as a sketch, but they are brutal once tooled. You have to see the true map before you build.